Hello. Welcome to Law Index 8, where we continue building a self-hosted compiler targeting WebAssembly. And today we will be actually learning how to build a WASM module. So first off, there is a bit of changes since previous devlog. Basically, I moved a separate branch into examples folder, and so we'll be working there. So let's switch to that folder. I am also now using code remote tunnels, this thing, instead of VS Code for web, because it has a bit better experience, but I will still be using all the features from VS Code web only. Yeah. Also, last time we were starting with reading files and parsing command line arguments. I decided that it's not the best start, so we will instead be starting with building WASM modules. So first off, let's create a module called Law Core, where we will be having all the core functionality. So let's see, we probably want to include standard library, and let's create a struct called law context. Here we will just put all the global context that we will need for building WASM modules and everything else, like including files. So let's create a small helper for creating the context. It will return a reference to the context. And we will store it on the heap. Okay, so let's create the context in our main function. Let's include the core module. Yep, so now we have our low context where we will be putting global stuff and so on. So we want to build WASM modules. So let's look at what a WASM module is. For that, let's Google up WASM spec. Here we go, WASM WebAssembly specifications. I will be using the Web3C version because it has better search functions. Basically, you can just use Ctrl F and search on the page. Let's wait for it to load because it's quite heavy. And we are interested in binary format, modules, and the module section here. So let's see. To create a WASM module, we will do that in binary format. So WASM module in binary format starts with a preamble that contains 4-byte magic number, 0 WASM, and a version field. Here we can see the actual bytes that go there, and this is basically required for every WASM module, even the empty one. So let's go on and do exactly that. First off, let's create the WASM module, not the actual WASM module, but in the code, like a library. So let's create the WASM module struct, and let's have a reference to it here, WASM module in the context. We would also want to include WASM.load. Alright, now we need to create it. Let's also go on and create the helper for that. And let's include standard library here as well. So yeah, so we put the WASM module reference in the context and we create it here. Yep, so now the context has the WASM module. So what we want to do now is create a binary buffer. So that would be a vector of bytes. Let's just free it when we are done with it. And what we want to do is we want to print the binary to standard output. Print string binary as string. Yep, so now we create an empty binary and just print it to the string, to output string. Yeah, so now let's actually populate this binary. We will create a function called WASM module write, and that will take self and the binary. And it would actually write stuff to the binary. Let's see, context was module write to the binary. Like that. Yes, and let's write magic and version there. For this we would just, yeah, let's first create a function to make it a bit clear what we are doing, so that we will be writing the preamble. Self write preamble to the binary. And that would be a magic string here. Yep. And what do we do to write it to a binary? Because it's a vector, we can just push to it. We will push this byte sequence in here. That would write 0 WASM. And now let's also push the version. And the version is 01 because the WebAssembly binary format current version is 1. So let's do just that. So we've written magic and version bytes to the binary. let's test out that it actually works. Let's probably also include. No, it's fine. Yeah, let's test out that it works. We will use the web shell here, and we will run. Because the actual compiler is in the parent folder, I will be using the parent folder, low WASM, and we will compile our new compiler, and let's put it into low WASM in the current folder. So this is the new one, and the old one is in the parent folder. Yep, so it is compiled without issues. Let's see. Let's just run it and see what it does. And as you can see, it actually prints something. And that should be the binary representation of the WASM module. So let's actually forward it to a to some file. Let's call it goal 0. So our first goal would be to create an empty module. And here it is. Now to confirm that we actually created a valid WASM module, we will, by the way, all links will be in the description. Let's see. So we will use the WebIt, the WebAssembly binary toolkit, and this allows us to convert binary representation into text representation. It also validates the module, which is what we want to do. This program is compiled to different architectures, and it is also compiled to WASM, which is very convenient for us. So let's go on and download that here, and let's go and extract it. Like that. And inside we can see the binary folder, and here we see the WASM to what program. So we want to download that. Let's download it somewhere, and let's copy it into a folder here. So I will click upload. Yep, so here we have it, and because it's a WebAssembly module, same as a compiler, we can just run it in the web shell. So we will go run wasm to what, and it expects the file name, and let's move them to temporary folder. So now we have wasm to what and our first goal into a temporary folder, and let's run wasm to what with goal 0.wasm. And as you can see, we got the empty WASM module. Very good. So that was the first goal, and our second goal would be let's see, so that was the first goal, is to have a empty module, and our second goal would be let's say a function for getting the answer. and that is what we want to compile next. We won't be actually lexing or parsing this yet, but instead we will just focus on building a WASM module that will encode these operations. So for that we would need, let's close that up. For that we would need to do three things. First, we want to define the function type. So define function type. Second, we want to put some instructions inside of the function. Put instructions into the function. And the third thing and the final one, we want to export this function. So export the transfer function. Yep, simple enough. So all of these steps correspond to a different WASM module sections, and the WASM binary format is basically this preamble here with the magic conversion and then a sequence of sections. So what sections are we interested in right now? We are interested in type section. Let's start with that. Yeah. Probably would be easier to just go for, yeah. Type section. So the type section has the ID 1. It decodes into a vector of function types. Yep. So let's go on and see how we will create sections. Let's start off with adding the types section here. It will be what it is, a vector of function types. So it would be a vector of, let's create a type here, WASM function type. Right, we don't yet know what goes inside. And let's do it def here for vector of WASM type, of WASM function types. Okay, so we have the types vector. Let's go on and create it. WASM function type. Okay, so we got our types. Let's create a function for writing them to the binary. That would be write type section types section. Let's create that function types section. Okay, so first of all, let's see what we will be putting there. We will be putting function types, which is a struct of result type and yeah, I see. So a struct from inputs, basically a mapping from input types to output types. So we will just be storing input types and output types. Let's see what the result type is a vector of value types. So let's, yeah, a bit convoluted, but let's see. So we have inputs, vector of WASM, what is it? Value types, value types, and outputs. Let's also do that. Not even sure if that would be restruct yet. Let's just do something like that. Yeah, so what this is, just a bit of an explanation. So there is no generics in the language yet, or maybe there won't be any generics at all. So basically, instead of just putting the vector without specifying what will be inside, I'll just create a type definition that would just correspond to a vector but with a more descriptive name. And this is just basically extends the symbol, so we can put anything here it's allowed. It would be just a different symbol. So this way we can kind of mimic generics, but yeah, which is much easier than actually implementing generics. So yeah, so we have our WASM function type, and now we want to know what the WASM value type is. Let's go and see that. And there is a union of different types, so we are interested in number types for now, and that is a byte. So okay, I was right. So WASM value type is a byte, and let's create a type def for i32 because we want our function to return that. So i32. Okay. So let's go on and encode that into the WASM module. Let's first make sure that it is actually created here. Yeah, it is actually created. All right. So populate WASM module here. Yep, so what we want to compile is this. The function type would be from empty inputs to a single i32. So u32 and i32 is the same, it's just a different one in the language itself to have a bit more type safety. Yeah. Yep. Context WASM module types push WASM function type. So we are expecting inputs. And outputs. Let's see. Let's probably create it here. Let get answer function type. Let's maybe create a function for that. function goal 1. Let's take the context. All right. Now we don't need the comment. And the outputs would have a single I32. Let's maybe format it like that so we can see it. Or make it like that. Alright, so we populate what we want for our second goal of compiling this. That is for the types. Now let's see how we will actually write that into a binary. So write type section. Type section. So what is a section? The section is a byte representing the number of bytes in the section. No, first one is basically n is the number of section. So the number of type section is 1. So let's actually go on and do that. Type section U8 is a byte. Section types. So that is the section with ID 1. So let's go on and push the section type. Valid arguments. Interesting. Yes, it's not a byte s 8 0x. Let's have it like that as a byte. Or maybe just one. So that is the type section. Here we put the section number. Now we want to write the section size, and then the section bytes buffer, basically. So to write section bytes, we would want a buffer somewhere. And because we write the size first and then the buffer later, we cannot really know its size beforehand. So let's actually create some kind of temporary buffer. Let's call it section buffer. Same vector of bytes. Now actually we want to do it like that. So we write our type section into the temporary buffer, then we would write the code of the section, and then we write the lengths. So let's see, to do write section lengths, and then write section bytes. Let's also call that out, because that's not the full binary. Let's see, so writing section lengths. And here is the first a bit annoying part. So all integers in binary representation in WASM are encoded using LEB128. So let's open that. Oh no. LEB128. So that is a variable length encoding that will use less space for encoding numbers than it can. Basically, here you can see how it works. So you have this number in binary, then you pad it to 7 bits, then you split it into groups of 7 bits, and then for each group you add a 1, saying that is the continuation of the group, and then the last one says 0, meaning there is no more groups. Then you encode that into bytes, so that is 8 bits would be a byte, and then you basically dump it into the output stream in reverse. So implementing this is not that simple, so I will just find the reference implementation somewhere, and I've used this one, which is pretty nice, but it is also padding to some bytes. We will not be padding anything. So let's see how we can write the integer in LEB128 encoded. For that, I've prepared the already made function that is basically writing this into the low language. Let me find it real quick. Okay, here I found the function. It was not that hard to rewrite, but yeah, writing that from scratch is not that simple. So we will use that to write all integers into the binary. So let's go on and use it. Write unsigned LEB128 integer into the binary. And the first one is the section length. So that is the section buffer size. And then we want to append the section buffer to the binary. So we'll basically write all bytes from section buffer into the binary, and that will also clear the section buffer so we can reuse it for other sections later. Yep. So let's also not forget to clean it up. And we're done with it. And that is the type section here. Let's do it like that. Alright, that should be okay. Now we actually need to write the contents of the type section. And let's see how that looks like. Don't need LEB28, 128. So here the type section is a vector of function types. So let's see how we encode vectors. And vectors are similar to sections, so you have the vector lengths and then the actual contents. And the vector length is in LEB128 again, so we will be using this quite a lot. So we will write types size first, and then we would write, yeah, then we need a loop for I in 0 to type size. So for each type we would write, oh, let's see, function type. That function type equals types that function type. Okay. So we write this byte, that means that it is a function type. So let's do that. So 0x60 is the function type identifier. And we are putting into a temporary buffer here, so that is the function identifier. And now we want to go the result type, which is here, and that is also a vector of value types. So let's do the same here. That is function type inputs. Let's then do another loop. Here for each input. Input type. So we get each input type and then we just write it to a binary, I guess. Yep, the value type is a byte, so we just write it like that. Push input type. Alright, so we've written all the inputs and now we do the same with the outputs. And this should be, let's see, let's double check. So we first write the lengths of the types, then we write each type inside of it. We say that it is a function type, then we write inputs and outputs. This checks out. Alright, let's try to run it and see if that is correct. First we want to recompile our new compiler, and now we run it, and let's output it to goal1.wasm. It is not the full goal one, but it's a only types. Let's see. So now we can run WASM to what, and as you can see, it was written successfully. Everything is valid, and here we have our function type. As you can see, there are no names here, so all the types in the WASM module are referred by their indexes. So this one is index 0. So yeah, so when you write a language, you need to keep track of indexes basically. In the code there will be names, in the binary there will be indexes. Yep, let's proceed with other sections. So this one is done. Now we want to, yeah, let's first maybe export the function, probably. Let's go there, because it's less stuff here. Let's see. So for that we need a export and export section. Let's see, here it is, export section. It is similar to the type section. It has index 7. Let's go on and do that. We have types, now we have exports, index 7. Let's just copy paste this for the exports. Let's copy paste that as well. Right, exports section. Yeah, let's also do here for write codes, write function instructions. You don't know what that section is yet. Alright, so the export section, we probably want to have exports defined here. Exports, that would be a export, so let's call that WASM export. WASM export. Let's create all the exports here. And let's see what we need inside of the WASM export. So it is either, alright, so export is the name of the export and then export description. The name is a name, which is a vector of bytes containing the Unicode, UTF-8 encoding of the name. Okay, so that is basically UTF-8 string first, which also contains which is a vector of bytes which contains the lengths first, then bytes after that. So a name and then export description, which is either one of those. We are interested in the function, so we will be using 0 and then function ag, and this one is basically just the function id, so it's a integer. All right, so here we want the name and the interesting, so all of them are ags, and then there is an export type, so let's have some kind of a type. Probably cannot use that, let's call it export type. That would be WASM export type, and then the export like item index, let's call it item. So we are exporting items, there is an item type, an item index, index is u32, and the export type is a byte, and the export type for the function like that would be 0. Yep, the function index here would be 0. What else do we need? So item index, item type, item index, that's probably it. Let's go on and add the export. Context, WASM module, exports, push WASM export. Let's see, WASM export. So that needs name, type, and index. Name be string. The name, let's just hard code it here for get answer. What else do we need? We need item type and item index. Item type is WASM export type function, and item index would be 0. Yep, and I messed up the types over here. Alright, so that is it for exporting the function. Let's see how we actually write it to the binary. So this would be exports. That would be export. Let's call it export underscore to not mess up with keywords. Let's see, so here we iterate through all the exports. That would be WASM export. So the export would contain the name. Let's see how we can write that. So we would push, let's see. The name is have push all function. That would be export name as export name size, and let's actually see what that accepts. Vector push all. So it accepts some items and then items lengths. So that would be name data and name size. Not the best API, but it works. Alright. So that will push all the bytes from the string into the temporary buffer. And now let's copy that here. Now we push the function, this one, so the item type, export item type, and then we push, not push, but we write the user32 index of the item. Like that. So that should be exporting the function. Let's see if that works. Might not work, but let's try it out anyways. Low WASM. Valid alignment. What is this? Yeah, some problems. Let me check. Alright, so there was some problems with alignment in the struct. So basically, if I put the byte in the struct, I actually need to align it to a integer, so to 4 bytes. I will look into that in the future, but for now I'll just have this as a user32. Okay, so I tested it out, see if that works. So basically recompile the compiler and run it, and it outputs something, but that does not, yeah, that's it. So as you can see, there are some problems with what is outputted here, and I figured it out that I am forgetting a, so basically when you encode a string, you have a vector of bytes, and that first needs its length, which I forgot. So let's write that here. So first we have export name size written, then it's bytes, then item type and item index. Alright, let's play recompile and see if that works. I forgot to actually do that. So temporary goal 1 WASM. Function variable out of range 0 max 1. So my guess is what that means is we are trying to export a function which does not have the code defined yet. So it is basically empty and we try to export it, which, yeah, makes sense. So let's proceed to writing function instructions. And the section for that is Let's see all these sections. Binary, text format, okay, binary format, sections, here we are. And the section for instructions is, I think, the function section, or code. What is the function section? Alright, so I'm missing another section. So another section here is the function section. So 3, 4. So when we define the function type, then we actually need to define the function and define a function with type 0, and that goes into the function section here. A function section has index 3, so let's go with the function section. So first we go types, then we go functions, right, functions. Types, functions, so functions index is 3, and that basically just is a vector of types. So it's basically a mapping from function index into the type index. So let's see, that should be a non-variable functions. Functions. Right, now we need that. So we'll be writing function section, and yeah, that would be just a vector of integers. So let's just do a vector of integers. We also don't have a type for that yet. And let's create it here, functions. So for our first goal, we want to have a find function. So its index would be index 0, and its type will be 0. Let's just do it like that. Functions push 0. So the function with index 0 will correspond to type with index 0. That makes sense to put it here first. Alright, so now for actually writing that into a binary, so that would be function index types functions, and that should be just like that. We 32 function type. So yeah, so just a vector of type indexes, which is just an integer. Alright, so we've written the functions. Let's see if that actually changes the error. And yep, now we get a new error saying the function signature count is not equal to function body count, which also makes sense. So we have a single function signature, which is in this section, but we don't have any instructions for it defined. So let's proceed with that, and that section is called code section. So the code section is a vector of code entries that are pairs of value type vectors and expressions. They represent the locals and body field of functions. Alright. And the type fields of the respective functions are encoded separately in the function section. Yes. Okay. So the code section has index 10. Let's start with that. Codes. Index 10. Let's maybe align that. Let's see. So what will be inside of the code section? There will be a code scene, which is a vector of instructions. No. Interesting. Yeah, as you can see, deciphering the documentation is an interesting task, but yeah, you have to do that eventually if you want to build it. The WASM binary representation. Another approach, by the way, is to use the text notation, the one that you get from WASM to what, but then converting it from the textual representation into a binary, you would need to have separate tooling, and yeah, having compiler in two parts is not a great idea. So we want to limit the number of moving parts. So we'll just output the binary format, and the binary format is the one that actually executes. So yeah, we just have to figure this out. So yeah, let me think about it a bit. Alright, so I had to read through this again and also look into how I implemented that earlier. So basically what this code entry is as it says, a pair of locals and body. And what the size is basically the total size of locals and the body. So this is like another section, a subsection, and that is its size. And that is basically, yeah, like a section, the code size is basically used for skipping that, for like when you read the binary you can skip stuff. and so that is why you put the size here. So for that we would need another temporary buffer, because we don't know the size before we write it somewhere. So yeah, it would be a bit more complicated than other sections, but let's do that anyway. So section, yeah, first of all let's probably define what goes in there. So functions, that is functions, that is types. Now we want codes, right? Codes, vector of WASM code. So what is a WASM code? Let's see, codes, WASM code. Alright, so what is in the WASM code? Size we will be calculating when we write that, so that would be a sequence of vectors of locals, I guess. Locals. No, actually it's just a vector of locals. So how that works is basically for each a type of local you have its, yeah, let's just skip it for now. So basically we don't use any locals here. There's just, we just have a single constant integer. So let's ignore that. So an empty vector is encoded as a first you encode its size and then its bytes. So we will just write 0 for the locals. So we don't need to store locals. So let's just say to do add locals. And then the expression, we want that expression. So each function body is a single expression, I guess. Yep. And the expression is basically a instruction sequence, which for some reason does not have a size, but I guess that's why you need a size here. So yeah, let's see. So we have an expression which would be a WASM expression, and that is struct WASM expression. Yeah, this is a bit of a mess with these definitions. I will probably clean it up later. So we have WASM expression, and that is actually just a type def for a vector of instructions. So let's just ignore it and just go straight to WASM instructions. Let's have its version of the vector, and the WASM instruction is, let's see, what is the WASM instruction? So a WASM instruction can be, so first it has the op code, the operation code, and then some optional parameters. It's probably won't be an easy way to encode that into a struct, We'll probably need some unions and stuff like that. But for now, let's just have a hard code there for that. So we will have an operation code, and then we would have, say, return. Now let's see. So what do we need? So the instruction here, we have a single instruction. Actually no. So this is two instructions. 42 is the i32 const instruction. Let's see if we can find it. i32 const. Yep, here it is. So this one will just create the integer and push it on to WASM stack. So we want that. And for the integer, you have this value, basically, which is i32. And let's just say we would have it like here, i32 const value. Yeah, this is basically temporary to find the better representation. And the OP code will be the operation code. So let's actually see how we will build that. So context, WASM module, codes, push, WASM code, WASM code. Let's see. So we need the expression, and that is, let's see, let expression WASM instruction. So it is the reference. Here. Okay, so we create the expression and we push it into codes. At index 0, that would be our first function, which we only have a single one, so that works out. And let's see what we'll be pushing into the expression. WASM instruction. WASM instruction. So the first one will be OP code. Let's see. So first we want the i32 const. That would be this. Yeah, and because we have problem with to do use u8 when align and it's fixed. Yeah, so we'll have a problem here if we'll use u8 here because of the alignment. So let's keep it as a u32. So that would be the OP code for i32 const, and the i32 const value would be 42. So that is our first instruction, and the second instruction would be to return. We want the explicit return. Let's see. Read. I think it's called. Yeah. Let's see. Code section. Expression. Instruction. So here's the return. it only has the operation code here. So this will be I32 const, and this one is return, and this one we just ignore for now. Yep. So let's see. We put that into WASM module. Now we actually need to write this section. Section name would be func, no codes. Right, code section. Types, functions, codes. Alright, and this will be the hardest section to write. So let's see, first one we would get the code, codes, get code. So we get our code entry, and now we want to, let's go back. So yes, a vector of code entries. So first we write its size, and then we write each code entry. So for each code entry we would have a temporary buffer. So let's call that let code buffer. And that would be a vector of bytes. And then we also free it at the end. So here we'll be pushing stuff into the code buffer. Let's see. So it first goes locals and then expression. So locals would be 0. Code buffer 0, so that is locals count. And then we need the expression, and that would be another vector. That would be code expression instruction. All right, now this wasn't instruction. All right, so we get each instruction. So first we write locals, then instructions. And then, so basically if instruction OP code is this, let's just hard code it before the better solution arrives. So if it's the I32 const instruction, we would write both OP code and the value. So let's do that. we would push into the code buffer, instruction, value, I32 const value, and here would be instruction OP code, and that is push a single byte. Alright. And if it's anything else, let's just do that like now. Let's actually have it like that. So if it is a return, then we just push the OP code. And let's put a to-do here as well. To-do handle other OP codes. Okay, that should be enough to... No. So, yeah, so we write everything into a temporary code buffer, but now we actually need to write it into a section buffer. So let's do that. So first thing, we write the code size. Okay, that would be code buffer size. And then we do the same thing as with temporary sections. We append the whole buffer there. And that should be it. Let's see. Let's put that into temporary goal 1, and then we run WASM to add. Function body must end with end OP code. Okay, so basically all expressions are a sequence of instructions and then the end operation code. So let's see, where do we put that? So number of locals and expression, and here we would put the end operation code. And operation code. Let's see. Section export out of order. All right, so all the sections need to be written in the order of their indexes. So first goes types, functions, exports, and code in our case. So let's see, types, functions, exports, and codes. So go types, functions, yes, then goes exports, and then codes. Let's update that. Go on. And finally, here we are. We created the WASM module corresponding to this. So we created the function type here, which takes nothing as the input and returns a single I32. Then we created the function with index 0, and its type is also 0, so it corresponds to that. The result is I32, is duplicated in the text representation. Then we have our instruction I32 const with value 42, and then we return this. And finally, we also export that function. So yeah, that is all it takes to create the WASM binary. Just 200 lines. Believe it or not, this is actually mostly the whole complexity of writing the WASM binaries. Basically, you just go through the spec, see the section, write the bytes in the correct orders, and that's it. So to create the simplest function, you need about 200 lines of code. And if we go to existing implementation, it's kind of apples to oranges, but the final, let's scroll to the end. So the final module writer would be about 600 lines of code, give or take. So yeah, not that hard to implement yourself. Yeah. Let's also do one more thing. We see that it is written like that, but we probably want to actually run it and see that the module we created actually works. So yeah, let's see. Let me set up the environment real quick. Alright, so I wanted to, let's actually mark that as done. So we did all the 4 sections. And yeah, so to actually run this WebAssembly module, we can either go and hook up the web server and host this, and then use some JavaScript to load and invoke the function, which is probably a better test, but instead I cheated a bit and we can actually use WASM time to run the function exported from there. And let's go on and do that. And it complains a bit about that it won't support invoking functions like that in the future, but never mind. And here is actually the output of the function. So we created the working WASM module in about like 200 plus that plus that, so in about 300 lines of code in a C-like language, which is not bad. Yeah, that's it for this devlog. In the next one we will be probably going for a bit more ambitious goal 2, where we will try to do a hello world using WASM. But for now, that's it. So yeah, bye.